This is a continuation of logistic regression, part 7. In part 6, we discuss square statistics and ultimately we get this form. We explain this via an example. Suppose we have n observation. There are two covariates or two explanatory variables. And each covariate have two labels. So we have total number of groups equal to 4, and we divide n observation into 4 groups, and first group contain n1 observation, second group n2, third n3 and fourth n4. This is the first group, second, and this is fourth. In first group we have two type of response, that is 1 or 0. So number of ones in group 1 we denote O11, and in group 1 number of 0 we denote N1 minus Y1, which is O12. Similarly, we define O21, O22, O31, O32, O41, O42 and compute T square M1. Now, sample size for approximate chi-square d square, we know for 2 cross 2 table, contingency table, for chi-square approximation, for the deviance or likelihood ratio and Pearsonian chi-square to be valid, we should have 75% of the EIK should be greater than equal to 5. In terms of logistic regression, EI1 Ni pi I hat, this should be greater than equal to 5, and EI2 Ni 1 minus pi I hat, this should be greater than equal to 5. Now if we add these two value, EI1 plus EI2, then you get simply small ni, and that should be greater than equal to 5 plus 5, 10. So Ni should be greater than equal to 10. Thus, as a rough rule of thumb, for chi-square approximation for the deviance, for the deviance and Pearson's chi-square to be valid, we should have %75 of Ni should be greater than equal to 10. That means, suppose if your capital I is 100, that is there are 100 groups, then out of 100 group at least 75 groups size should be greater than equal to 10. However, Ni is often small. For example, the covariate or explanatory variable may be continuous. So this implies Ni should be 1. Secondly, the model may a lot of covariate or explanatory variables, so that very few individuals have the same pattern, and most individuals will have different xi curve. In this case, the deviance and Pearson's chi-square will not be approximately chi-square. For example, consider esophageal cancer data. There are 3 covariates: age, alcohol, and third is tobacco. Alcohol has 4 levels, age has 6 level, alcohol has 4 level, and tobacco has 4 level. Then we have total number of groups is 6 into 4 into 4, that is 96 groups or strata. And we observe that 8 strata have no observations. So we remove this 8 strata, then we have 88 strata for this model, and we have 975 total number of observations. Then if this is all approximately 11, so if we have 11 observations per stratum or group, then this appears to be a good number. However, when looking more closely to the data, we see that only 31 of the 88 strata, which is approximately 35%, where Ni greater than equal to 10. So we need little care, or we may want to be little careful when using d-square. For Bernoulli data, parameter the parameter estimates are okay, but since each group has only one observation, that is Ni equal to 1, d square will not be asymptotically chi-square, and could give very deceptive idea of fit. In this case, you could do as before, fit a broader model, then given a model but not to the saturated model. So we fit a broader model, then the given model but not the saturated model. So here we do not use saturated model, we use broader model and compare with your given model. And in that case, our likelihood ratio statistics is given as follow. And here I mention this one point, that is this type of model is called nested model. So likelihood ratio statistic for nested models Suppose yi follow Bernoulli pi I, then model 1, or simply denote it M1, that is pi I equal to e to the power beta naught beta 1 curl prime xi curl by 1 plus exp beta naught beta 1 curl prime xi curl. Then model 2, which is the border model, we denote it by M2, and pi I here equal to exp beta naught beta 1 curl prime xi curl beta 2 curl prime zi curl by 1 plus exp beta naught beta 1 curl prime xi curl beta 2 curl prime zi curl. Now our hypothesis is beta 2 curl equal to null. Deviance d square is start of like a sum of square error in the given model versus the saturated, and a smaller model will always have more the same or more error than the bigger model. So the deviance denoted by delta d square M2 given M1. So this is nothing but a d square M1 d square M2, which is similar as conditional SSE of M2 given M1 if we consider linear model case or linear regression model. So this is nothing but a 2 log, the first term is 2 log L beta hat for saturated model minus log L beta curl for M1. Similarly, this is for this term minus 2 log L beta hat for saturated minus log L beta tilde for M2. So simply this is equal to this, and this is nothing but the change in d square for model 2 versus model 1, and If the smaller model fits in large samples, delta d square m2 given m1 approximately chi square m, and m is a m parameters are set to 0 in the smaller model. We note that even though we need binomial data, that is ni to be large for d square to be approximately chi square, the same is not true for del d square. Next, each individual in the study could have a different xi. That means ni equal to 1 and del d square will still be approximately chi square test statistics for beta 2 equal to 0. Since log L beta hat given saturated subtracts out in the difference. So I repeat this again. Even though we need binomial data ni to be large for d square to be approximately chi square, the same is not true for del d square. Next, each individual in the study could have different xi curl. That means ni equal to 1 and del d square will still be approximately a chi square test statistic for beta 2 equal to 0, since log L beta hat curl saturated subtracts out in the difference. Using difference in d square, using differences in d square, using differences in d squares is just a trick to get the likelihood ratio statistic to log L beta curl tilde given m2 minus log L beta tilde curl given m1. In particular, the log likelihood for the saturated model subtracts out and does not affect asymptotics. Basically, regardless of size of nj, if you are comparing m1 pi I exp beta naught plus beta 1 prime xi plus exp beta naught plus beta 1 prime xi with m2, where pi I equal to beta naught plus beta 1 prime xi plus beta 2 prime zi given 1 plus exp beta 1 prime xi plus beta 2 prime zi. A Taylor series approximation can be used to show that del d square m2 given m1, if you use only one explanatory variable in m1, then this approximately beta 2 hat by estimate of variance of beta 2 hat whole square, which is approximately chi-square with 1 degrees of freedom. Please stay with us. We will continue this topic in our next session. Thank you.